Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about a two species competition model and a discrete case. So, let us consider that in a jungle there are two species, say lion and tiger, and they compete for food, space. So, their common food may be deer or any other animal. So, how this model will look like in a discrete case. So, if we consider say B to be the number of lions and G to be the number of tigers in n plus 1 at time. So, B n plus 1 will be the number of lions in time n plus, suppose they grow at a rate alpha 1. Then there will be an interaction between the lion and the tiger, rather a competition for food, and let that be at a rate beta 1. And ultimately, the same species lion will also compete for food, and hence that happens at a rate gamma 1. In the similar manner, the tiger equation is going to be the number of tigers in n plus 1 times in the nth time, say they grow at a rate alpha 2, they are competing for food at a rate beta 2, and they are competing about each other at a rate gamma 2. Now, if you recall, we have something called intraspecific competition and interspecific competition. So, intraspecific competition means that they are competing among each other for food. So, in this case, this term is the intraspecific competition, this term is the intraspecific competition, and they are happening at the rate of gamma 1 and gamma 2. And interspecific competition is when they are competing for food with different species. So, in this case, the lion is competing with tiger and tiger is competing with lion. That is interspecific competition, and they are happening at a rate of beta 1 and beta 2. These are the growth rates for the lion, this is the growth rate for the tiger. So, once this model is formed, obviously you will go and look for its equilibrium solution. So, the equilibrium solution will be given by no change from n to n plus 1th generation or time. So, this n plus 1. So, we replace b n plus 1 equal to b n by b star and g n plus 1 g n by g star. You substitute them here and you get b star equal to b star plus alpha 1 b star minus beta 1 b g minus gamma 1 b star square. These two cancels. I take b star common and I get alpha 1 minus beta 1 g star minus gamma 1 b star equal to 0. From the second equation, similarly, I will get g star equal to g star plus alpha 2 g star minus beta 2 b star g star minus gamma 2 g star square. These two cancels. You take g star common, alpha 2 minus beta 2 b star minus gamma 2 G star. So, from equation 1 and 2 we have to find the equilibrium solution. So, you have B star alpha 1 beta 1 G gamma 1 B, beta 1 G star minus gamma 1 B star equal to 0, and you have G star alpha 2 minus beta 2 and gamma 2. So, beta 2 B star and gamma 2 G star equal to 0. Quick check, beta 2 gamma 2 G star. Yeah. So, from here beta star equal to 0, and if you substitute beta star equal to 0 here, you will get G star equal to 0 and alpha 2 minus gamma 2 G star equal to 0, which will give G star equal to 0 and G star equal to alpha 2 by gamma 2. So, combining this and this two, we will have our solution in the form B star G star, where B star is 0 0 and another value is 0 alpha 2 by gamma 2. So, if B star equal to 0, you have these two solutions. And also we have alpha 1 minus beta 1 G star minus gamma 1 B star equal to 0. Now, from here you have G star equal to 0 and alpha 2 minus beta 2 B star minus gamma 2 G star equal to 0. Now, if G star equal to 0 and you substitute it here, you will get B star into alpha 1 minus gamma 1 B star equal to 0. This will imply B star equal to 0 and B star equal to alpha 1 by gamma 1. So, if I combine these two, I will get 0 0 and alpha 1 by gamma 1 comma 0. 0 0 is already there, so we accept this. So, right now with this you have 1, 2 and 3 equilibrium solutions. The final one will come from solving this and this equation. So, we write them as gamma 1 B star plus beta 1 G star minus alpha 1 equal to 0, and beta 2 B star plus gamma 2 G star minus alpha 2 equal to 0. You can solve by any method. I use method of cross multiplication. So, B star by G star by 1 by. So, if I take B star, then this by this. So, alpha 1 gamma 2 minus alpha 2 beta 1. For G, it will be reversed. So, this multiplied by this. So, alpha 1 gamma 1 alpha 2 minus alpha 1 beta 2, and this one will be gamma 1 gamma 2 minus beta 1 beta 2. So, your B star is equal to alpha 1 gamma 2 minus alpha 2 beta 1 by alpha gamma 1 gamma 2 minus beta 1 beta 2, and your G star is gamma 1 alpha 2 minus alpha 1 beta 2 by gamma 1 gamma 2 minus beta 1 beta 2. So, you have 4 points of equilibria, and let us now go for the stability analysis. And for the existence of this point of equilibria, this is 0 0, this one is clearly positive, this one is clearly positive, and for this both of them either have to be positive or both of them have to be negative, or both of them have to be positive, both of them have to be negative. because B star and G star cannot be negative. And in these two equations, the parameters are alpha 1, beta 1, gamma 1, and alpha 2, beta 2, gamma 2, and all of them are positive. So, after getting the equilibrium solution, we go for the stability analysis. So, you have 0, 0, you have alpha 1 by gamma 1, 0, you have 0 alpha 2 by gamma 2, and B star G star, where B star and G star have been given in this form. Now, say 1. Your equation was in the form Bn plus 1 equal to Bn plus alpha 1 beta n minus beta 1 Bn Gn minus gamma 1 Bn square. So, you take this function in the form of say f1, which is b plus alpha b minus beta bg minus gamma b square. Similarly, your f2 is going to be g plus alpha 2g minus beta 2 bg minus gamma 2 g square. So, the coefficient matrix is going to be, so I differentiate with respect to b, 1 plus alpha 1 minus beta 1 g minus 2 gamma 1 b at the equilibrium point. With respect to g, this is minus beta b star. This is again with respect to b, minus beta 2 g star, and then with respect to g, this will be 1 plus alpha 2 minus beta 2 b star minus 2 gamma 2 g star. So, this is the coefficient matrix at the equilibrium point B star and G star. Now, let us take 0, 0. So, this is 1. So, you substitute this 0, 0 here and your coefficient matrix becomes 1 plus alpha 1, 0, 0, 1 plus alpha 2. And clearly the eigenvalues are 1 plus alpha 1 and lambda 2 is 1 plus alpha 2. So, the modulus lambda 1 is greater than 1, modulus lambda 2 greater than 1. So, the system is unstable at 0, 0. So, 0, 0 means both the species dies and nobody wants an extinction. So, that is why it is obvious, and as the model suggests, the system is unstable. Let us move to the second equilibrium point, say alpha 1 by gamma 1, 0. So, your A, which is 1 plus alpha 1 minus beta 1 g star minus 2 gamma 1 b star minus beta 1 b star minus beta 2 g star and 1 plus alpha 2 minus beta 2 b star minus 2 gamma 2 g star. So, you substitute this value here and you will get, so g star is 0. So, 1 plus alpha 1, this vanishes, minus 2 gamma 1, and b star is alpha 1 by gamma 1. This is minus beta 1 alpha 1 by gamma 1. This value is 0. This is 1 plus alpha 2 minus beta 2 into alpha 1 by gamma 1, and this vanishes. So, you get A is equal to 1 minus alpha 1 minus beta alpha 1 by gamma 1, this is 0, 1 plus alpha 2 minus beta 2 alpha 1 by gamma 1. So, the eigenvalues again, lambda 1 is 1 minus alpha 1 and lambda 2 is 1 plus alpha 2 minus alpha 1 beta 2 by gamma 1. For the system to be stable, you have to have mod of this must be less than 1 and mod of this must be less than 1. So, if this condition is satisfied, we can see that in this case the lion species survives, whereas the tiger species goes to extinction. So, this is stable provided these two conditions holds. In the similar manner, if we take 0 alpha 2 by gamma 2, you will get your coefficient matrix to be 1 plus alpha 1 minus alpha 2 beta 1 by gamma 2, 0 minus alpha 2 beta 2 by gamma 2 and 1 minus alpha 2. So, if you see the eigenvalues, again the eigenvalues lambda 1 is 1 plus alpha 1 minus alpha 2 beta 1 divided by gamma 2 and lambda 2 is 1 minus alpha 2. So, if you are wondering that how I am directly writing the eigenvalues, it is nothing but this quantity minus lambda, this is 0, this is minus alpha 2 beta 2 by gamma 2, this is 1 minus alpha 2 minus lambda. Since this is 0, this minus this is 0 and hence lambda 2 is 1 minus alpha 2 and lambda 1 is whatever this quantity. So, straight away I write these two values. And this system will be stable if your lambda 1 mod of lambda 1 is less than 1 and mod of lambda 2 is less than 1, just like the previous case. And the final one, B star and G star. So, these are quite complicated values you can do of your own. You substitute them in place of B star and G star, and whatever the eigenvalues you get, the modulus of that must be less than 1. This I leave it to you for your calculations. Now, let us look into the numerical solution of this particular model. So, how the model behaves, what is the dynamics of the model for various values of alphas, betas and gammas. Okay, I have this spreadsheet of Microsoft Excel. Quickly I write it here. You have B n plus 1 which is equal to Bn plus alpha 1 into Bn minus beta 1 into Bn into Gn and minus gamma 1 into Bn square. So, you have this equation, and similarly I can get the equation for Gn also. So, this is your B n plus 1 and this is your G n plus 1. Okay. let us quickly write what is alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2. So, alpha 1 is 1.9, this is 0.0003, this is 0.03003, alpha 2 is 1.1, beta 2 is 0.0001, and gamma 2 is 0.001. I highlight them a little and change the font so that it's easy to see, put them in the middle. Okay. So, I get the initial values of both the species to be same, say to be 200, and then calculate this. So, this is equal to Bn, which is this, plus alpha 1, which is 1.9, and it is a constant, multiplied by Bn, so again 200 minus beta 1, again it is a constant, multiplied by Bn multiplied by Gn minus gamma 1, which is again a constant. So, I put a dollar multiplied by Bn square. Okay, to calculate this value, I put this is equal to Gn plus alpha 2, which is a constant, multiplied by Bn into Gn minus beta 2, again a constant, multiplied by Bn into Gn and minus gamma 2, which is again a constant, multiplied by G square. So, these two values have been calculated. So, if I want to solve them, go to insert, go to the chart and draw this. So, what you get here is two species competition model. Select it, go to series 1, edit, series 1 is lions and series 2 is tigers. So, from the graph you observe that for this particular set of parameters, both the species survives, though they have a competition in between them. Now, if you want to change the value, say if I change this value to 0.0025, so all you have to do is just click outside and everything changes automatically, and you just see the number of lions, they just go into extinct, whereas the number of tigers, they survives. Similarly, you can play with other parameter values and obtain different other dynamics. Let's now go back to our slides. We now look into the numerical solution that we just generated, and here the value of alpha 1 is 1.9, beta 1 is 0.0003, gamma 1 is 0.003, alpha 2 is equal to 1.1, beta 2 is 0.0001, and gamma 2 is 0.001. The initial values of both lions and tigers are 200 and 200. So, you see that with this parameter values, both the species survives and they reach to some steady state. Now, if we change the value of beta 1, say I put beta 1 equal to 0.0025, keeping all the other parameter values same, keeping all initial conditions also same, and we see that the tiger species goes to extinction, sorry, the lion species goes to extinction, whereas the tigers survive with beta 1 equal to 0.0025. Similarly, with another set you can show that the tiger species, they goes to extinct, where the lion species, they survives. However, we always maintain that both the species to survive as seen in our real life scenario in the real jungle. So, with that we come to the end of this lecture. In my next lecture, we will be talking about disease infection model in discrete case. Till then, bye bye.